Hi, ID Automata here with a video on optimization. We're going to try and fit some model data to some equation. This is the data set and the model that we're going to try to fit. What we want to do first is set up a function that will map our x values, our input values, to our expected output values, the xy pairs that we have. We'll do it like so. Then we will use the pandas library to import the data that we may use it for our optimization purposes. Something we can do before we continue is we can try and visualize our data. So here we are using the matplotlib library to plot the data before we continue with optimization. Next we'll be setting up our function that we'll be minimizing. Within the function there is the error term, which will be the sum of the root mean square errors that we will be calculating as we iterate through the set of x values that we have. So this error term that we will be using will be a measure of how close we are to the local minimum, or at least hopefully the global minimum is unlikely. And of course, as you saw in the dataset, it is impossible to fit all the data to a single line unless you're using an extremely high order polynomial. So we will not expect a zero term, but we will try and minimize it. Now that we have set up the minimize function, we'll be developing the rest of the code that we need to carry out the operation of optimization. So first of all, we'll estimate our initial values of the parameters for the model that we'll be using, the equation that we'll be using, that is. The next step is developing the boundary conditions that we have, or we may have. In our case, we do have some because we're using an exponential and we would like to bound the parameter that's attached to the power of the exponential. We're now ready to use the minimize function that we imported from the SciPy library. It takes in 4 arguments: the minimizing function, the array of parameters that we have, the method we'll be using for minimization, and the bounds that we've set up. We're using the sequentially squared programming method, which works for nonlinear cases such as the one we're using right now. So we're ready to go. We'll just run the function and see what we get as the output. The optimization worked. What we're looking for are those 6 values that we have at the very end there as the final set of parameters that will optimize our function and minimize the equation that we gave. We can also try and have a look at the equation with the optimized set of parameters, and we'll see it actually fits the data well enough, which is good enough for me. So, yep. Thanks for watching. Good day.